So in this problem, we have f of x is equal to natural log of 1 plus x cubed, and we saw Jasmine do part C, and she found that g of 1 is approximately 18 over 55. In part D, it says the Maclaurin series for g, evaluated at x is equal to 1, is a convergent alternating series with individual terms that decrease in absolute value to 0. So that particular sentence is telling you that what you have is a convergent alternating series with individual terms that decrease in absolute value to 0. In other words, the hypotheses of the alternating series remainder theorem are told to be satisfied. You have a convergent alternating series and individual terms decrease in value to 0. Then, according to this theorem, the absolute value of the remainder R sub n involved in approximating the infinite sum by the nth partial sum is less than or equal to the first neglected term. So the hypotheses of this theorem are satisfied, so we may use this theorem to do the work that we have to do for part D. And what is it that we have to do? We have to show that our approximation from part C must differ from g of 1 by less than 1/5. This is what we found in part C. G of x is equal to this power series with infinitely many terms. But of course, if we want to approximate g of 1, we can use an nth partial sum of this infinite series. And in part C, we use the second partial sum. So according to the alternating series remainder, if you have an alternating series, such as we do in representing g of x with a power series, we may approximate the infinite sum with an nth partial sum. But if we do that, we can find the remainder, or the difference between the infinite sum and our nth partial sum approximation. So g of 1 is representing our infinite sum of our series when it is evaluated at x is equal to 1. And the difference between that and the second partial sum approximation that we found in part C, which we can write the value 18 over 55, that the absolute value of that difference, called the second remainder, according to this theorem, has to be less than or equal to the first neglected term. And of course, if we're using the first two terms to approximate the infinite series evaluated at x is equal to 1, the first neglected term will be this one here. And we will, of course, evaluate that at x is equal to 1, and that would give us 3 over 17. To conclude, we need to go back to what problem D is asking us to do. It says, show that your approximation in part C differs from the exact value of g of 1 by less than 1/5. What we've been able to do is, using the alternating series remainder theorem, we've shown that our approximation in part C must differ from the exact value of g of 1 by an amount that is less than or equal to 3 over 17. How does that compare to 1/5? 1/5 is about 20%, or I should say 1/5 is 2/10, 0.2, and 3 over 17 is about 0.17 or 0.18. So 3 over 17 is actually less than 1/5. So we can write that 3 over 17 is less than 1/5. So if you look at this inequality, we're saying that the difference, the absolute value of the difference between the exact value of g of 1 and our approximation for it has to be less than 1/5, and that's what we wanted to show. Show that our approximation in part C must differ from the exact value of g of 1 by less than 1/5. We were able to do so by using the alternating series remainder.